Hey guys, welcome to my channel. This video is the first video in a series on the central limit theorem, understanding and proving the central limit theorem. In this first video, I will give you the statement of the theorem and we'll look at it and try to understand from a high level what it's saying. Okay, so let's go ahead and get started with the statement of the theorem. Okay, so let's go to the statement of the theorem. Here it is in all of its glory. If you are new to mathematics, none of this might not make a whole lot of sense, but that's the point of this series, is to help you to understand each and every part of the central limit theorem. Okay, so, and if you're not new to mathematics, if you're not new to statistics, then maybe I can provide some additional insight. Okay, or maybe you can put some additional insight in the comments. So let's just take a look at the theorem. Now, before I do that, what does the central limit theorem mean to most people? It's hard to say, but usually when I see the central limit theorem discussed or talked about in different forums with regard to data science or statistics, it essentially is people are getting the idea that if they collect enough samples from various population, then they can get a bell curve, basically. So not to sound cynical, but a lot of times it seems like a reason why one doesn't need to check for assumptions in parametric tests, something like that, along these lines. Okay, so that's my naive, unresearched perception, right? But that's not exactly what the central limit theorem is saying in essence. Now, there is some intuition into the idea that if you take enough samples of the sums of the results of random experiments, then it will eventually, as the number of sums that you take gets larger, you'll get more and more of a bell curve. So I think a lot of people might understand this in terms of the sampling of the mean, the sampling of the distribution means. So where you're taking samples, you're taking K samples from a population, and then for each of the samples, you create a distribution from the means of those samples, and that distribution, regardless of what kind of population you have drawn those samples from, the distribution of those means will follow a normal distribution, or in other words, a standard normal distribution. It's a little more precise than a normal distribution. Actually, the claim is that it's going to follow the standard normal distribution, which, as you may know, has mean equal to 0 and standard deviation equal to 1, if I'm not mistaken. Pretty sure. I hope so. I'm making this video. So so mathematically, what does that mean? So let's start with the statement of the theorem, like I mentioned earlier. So it says, let x1, x2, up to xn and beyond be a sequence of independent and identically distributed random variables where each xi has expected value equal to a mean mu, which is finite, so it's less than infinity, and the variance for each of our random variables, xi, is sigma squared, which is also finite. So if this is true, then the distribution of, now look what we have here. We have the sum of this sequence of random variables. And if I were to, let me just do something here to remind you of something you may be aware of. One thing that you might notice here, we've got an in here. We've got it in here. So let's see if I just removed everything like this, and you'll see why I'm doing this. It might look familiar. Do you remember the z-score formula? It's just x minus mu divided by sigma, right? And actually, should it be sigma squared? No, that's right. It's sigma. So the standard deviation, that doesn't look much like a sigma, right? It looks kind of like a 6. Try that again. So this is for one random variable. But here you can see we've got the sum of n random variables here. Right? And so here we've got mu times n, and then we've got our standard deviation times the square root of n. Okay, so that's just something I want to draw your attention to right now, and we'll explain it in more detail later on. So there's a similarity that you might notice between the z-score formula and this thing that we have created by taking a sum of our random variables. Okay, so x1, x2, we're adding together each of these random variables. Okay, now this term here, this expression rather, sorry, not a term, this expression converges in distribution. So we'll have to discuss what does converge mean if you don't know. We'll have to discuss what does in distribution mean. There are many different types of convergence. We have convergence almost surely, convergence in probability, convergence in distribution. And so we'll talk about the different types of convergence, and it may require that we look into analysis and the convergence of sequences of functions. Okay, so in order to be able to understand the proof. So this expression, which we've seen, is the summation of our independent and identically distributed random variables. And then it's essentially, we're scaling it, right? We're scaling it, subtract mu times n divided by standard deviation times square root of n. It will converge to the standard normal random variable as n goes to infinity. So as we take more and more and more samples, our distribution will start to converge to standard normal distribution, which is this. Okay, so this thing over here, this is the probability density function for the standard normal random variable. If I graph this in my calculator or in Python or R or wherever, you will see that it gives me the precise bell curve for the standard normal distribution when the mean is 0 and the standard deviation is 1. Okay. And so what is sort of amazing and encoded in the fabric of the cosmos, essentially, because this is so applicable in so many different disciplines and fields, from sociology to quantum physics, is that as n goes to infinity, the probability, so we can calculate the probability that the summation is less than some value a by integrating over this PDF from negative infinity to a. So in other words, we can use the standard normal random variable to calculate probabilities for the sum of these independent and identically distributed random variables. Okay, so that's the theorem. That's the statement of the theorem. What's the big idea, in my opinion, here is that we're able to collect these samples. It doesn't matter, if you'll notice in the statement of the theorem, it doesn't matter what sort of distribution these random variables come from. The only thing that we require about the random variables is that they come from an identical distribution. So it doesn't matter if the distribution is Pareto distribution, no. Doesn't matter if the distribution is exponential distribution, doesn't matter if the distribution is a gamma distribution, doesn't matter if the distribution is Poisson. I think it might be continuous, actually. So according to this idea here, we don't need to consider where or what type of distribution they come from, because the thing that's so powerful is that if we take their summation and then we scale it, sort of like a z-score looking like that, right? We can calculate their probabilities using this PDF. That's amazing. We can take, and this is one of the beautiful things about mathematics and statistics. We can get samples from any sort of distribution, and if they can meet these conditions, then we can calculate their probability using the standard normal distribution. Okay, so that's the statement of the theorem. In the next video, I'm going to keep these short, and in the next video, we're going to talk about basically each of these items that we need to understand in the theorem. So we'll talk about what is a random variable, just in case you don't know what that is. We'll talk about what is a sequence, what does it mean that they're independent, what does it mean that they're identically distributed. We'll talk about each and every point here that you need to understand. And then we'll talk about convergence, what is in distribution, and then what does this mean? So I think you know what this means. If I say it in words, it says that we can calculate the probability that this expression is some value by using you could use a z-table. Okay, so that's a layman's way to think about it, I think, if a layman can talk about the z-table. But in other words, we can use this distribution to calculate the probability, which is what we would like to do, right? We would like to be able to make inferences about population from our samples. And this gives us a way to do it using the standard normal random variable distribution. So we'll talk about that. And then we will have to talk about cumulative distribution functions, and we'll have to talk about moment generating function, because we will use that in our strategy of the proof. Okay. And so we're going to borrow an idea from analysis regarding convergence of a function and its antiderivative. And you'll see how that all goes together in the next couple of videos. So that's it for the statement of the theorem. If you have any questions, if you notice any inaccuracies, if I said something incorrectly, please put your comments, requests, suggestions, or corrections below. If you feel like it, like and subscribe. And thanks for watching. I hope this helps. And that's it for me, signing off.